In this lesson, we are going to review linear function. Let's recall what's a slope of a line. Well, slope of a line or a line segment connecting any two given points with coordinates x1, y1 and x2, y2 is the difference quotient. It's a quotient of two differences, difference between y's and difference between x coordinates. How does it look on the diagram? If we have two given points, and if we complete the right angle triangle by projecting those points vertically and horizontally, then the vertical change is measured by difference y2 minus y1, and the horizontal change is measured by the difference x2 minus x1. So horizontal change is also called the run part, and the vertical change rise part, or fall if the change is negative. In other words, slope is the ratio between the vertical change or change in y. Sometimes the change in y can be recorded as delta y, that really indicates the difference between y coordinates, over the change in x, which can be recorded as delta x, difference in x. So the slope, which is customary marked by a letter m, is either rise over run, or delta y over delta x, or the quotient of differences between y coordinates and x coordinates. Obviously, such slope exists as long as the first coordinates x1 and x2 are different. In case that the first coordinates of the 2 points are equal, then the slope is undefined. This is the case when the 2 points are positioned on a vertical line. Therefore, the first coordinates of such points will be the same, and the slope of a vertical line is undefined. Since we don't really run anything, we only rise. So division by 0 is impossible to perform. That's why the slope is undefined. So again, the slope represents the steepness of a line, or you can consider this as a change in elevation in respect to the horizontal change. Or we can think of a rate of change of y in respect to x, or simply think about rise over run. What's a line? A line is defined by the property that for any 2 points that belongs to the line, the slope between them is the same. So it is a set of points of a plane such that the slope between any pair of these points is the same. And a linear function is a function that can always be written in the form mx plus b, where m is our slope and b y-intercept. Here we have first example to practice how to calculate slope and what the slope really tells us about the behavior of the line containing the 2 given points. In example A, the slope is, according to our rule, difference in y coordinates. So if we start, let's say, with the first point 4 minus 4 over difference in x coordinate 3 minus negative 2, as you see, the numerator is 0 and the denominator is something else. So overall the slope is 0. What does this tell me about the line? Well, the line is horizontal. What about question B? Well, here we have slope equals. We can start with any point that we wish. Just for change, let's start with the second point. 4 minus negative 1 over, and now we have to start with the same point as in the numerator, negative 3 minus negative 5. So 4 plus 1 is 5 over negative 3 plus 5 is 2. So this is a positive slope, So the line increases somehow like this. And let's see what is the slope in example C. Well, since first coordinates of the 2 points are exactly the same, then according to our rule, the slope is undefined. So here the slope is undefined, which tells me that the line is actually vertical. Looks like that. Vertical line. In the last example, let's follow the rule of the slope. I need to make a difference between y coordinates, so f of 1 plus h minus f of 1 over difference in the first coordinate, so 1 plus h minus 1. Since 1 will disappear, then you really have the difference quotient f of 1 plus h minus f of 1 over h. And this expression is actually very important towards the calculus, because in calculus we'll be interested in difference quotients such that h will be very, very small, but you're going to calculate a lot of this kind of expressions. Forms of a linear function. How can we record a linear function? Well, the most popular and probably the easiest to graph form is slope-intercept form y equals mx plus b, where m is our slope and b is our y-intercept. But we have some other forms of a line as well. For example, slope-point form. This is a very useful form when you have one point given and a slope given. To write equation of a line, you just plug it into this formula and it will be enough to just simplify a little bit. So in this formula, x and y are variables, so you don't replace them. What you do replace is the coordinates of the given point, which is x1 and y1, and the given slope m. Finally, standard form of equation of a line. Any equation of a line can be written in a form ax plus by equals c. This is called standard form. So it's a good idea to be able to convert one form to the other whenever it's needed. Some special cases, a horizontal line can be written as y equals a constant, and a vertical line, x equals a constant. And here we have another example. Given the equation, this particular equation, find its x and y intercepts. Well, how do we find x-intercept? We set y to 0 and then calculate what's the remaining x. So if y is 0, this term will disappear and it's easy to solve the remaining equation in your mind. So x would be equal to 6 divided by 3 is 2. So x equals 2. Similarly, to find out y-intercept, we set x to 0 and then find out what's y. If x is 0 in this equation, so this term disappears, and when you solve it, it's 6 divided by -4, so it's -3/2. Now we should rewrite the equation in slope-intercept form and graph it. So to rewrite this, it's enough to solve for y. We could move the 4y to the right side and 6 to the left side, and then divide by 4. So 3/4 x minus 6 over 4 is 3 over 2. Now to graph it, we can follow the y-intercept rule. So we start with -3/2. Let's say it's somewhere here, -3/2. And we go by the slope 3/4. So 4 steps across, 3 steps up to get the next point. Since I want a little bit better precision, I will go 4 steps backwards and 3 steps down. And then take a ruler and draw a line. As you see, the y-intercept is indeed -3/2. So that's my y-intercept. And the x-intercept is 2. That's the x-intercept. Now, in order to write an equation of a line passing through two given points, the best idea is to use slope-point form of a line. Let's use it. First, we need to find out what's our slope. Well, the slope is the difference quotient. So it's 1 minus 4 over 3 minus -1, which is -3 over 4, -3/4. Therefore, the equation of the line will be y minus the y coordinate, let's choose this point because it seems to be easier, equals slope -3/4 x minus the x coordinate of the given point. Now we need to simplify this a little bit, so let's open the bracket, -3/4 x plus 9/4. And I want to move the 1 to the right with the denominator 4, so it will be 4/4. Okay, finally y equals -3/4 x plus 13/4, and that's our line. If we talk about lines, it's good to know how to recognize parallel or perpendicular lines. We know that parallel lines will have the same slope because they should have the same steepness, so they are parallel. Perpendicular lines, though, have slopes that are opposite reciprocals. Here on the diagram, we can see easily how come those are really opposite reciprocals. Let's consider this first line here. The slope of it is a over b. So that's the slope of the first line. If we rotate this line by 90 degrees, this triangle will be rotated as well, and it becomes a triangle like this, where this distance is a, however, it goes towards the negative side. So it's actually negative vector, -a. And that distance has a length b as before. So altogether, the slope of the new line is actually -b over a. It can be seen on this triangle or that triangle, still -a and +b. So in summary, if m1 and m2 represents the slopes of two lines, then as long as m1 is equal to m2, we can claim that the lines are parallel. To indicate that the lines are parallel, we just write this sign. And if we can claim that one slope is negative reciprocal of the other slope, then the two lines are perpendicular. This statement is if and only if, so it goes both ways. If they are perpendicular, then the slopes behave that way. Or if you can determine that the slopes behave that way, then the lines are perpendicular. The sign for being perpendicular is like that. Notice also that this equation is equivalent to saying that the product of m1 times m2, if you multiply this equation by m2, then this product m1 times m2 is equal to -1. So saying that two lines are perpendicular is equivalent to saying that the product of the slopes of those two lines is equal to -1. Okay, so find the equation of the line whose graph is parallel to the graph of the given equation and passes through the given point. So if I want the equation of a line that is parallel to the given one, I need to know the slope of the given line. To find slope of 3x minus 2y equals 5, solve for y. So we're solving for y. If you bring the 2y to the right and 5 to the left, you can see your equation in that form. Then divide by 2 and we have 3/2 x minus 5/2. Only 3/2 is of our interest. That's all what we take from this piece of information. So we're taking this slope and we want to write the equation of a parallel line. Therefore, our slope for a future line is indeed the same, 3/2. And our point that we are using is -3/4. Now we use slope point formula of a line. Use slope point form. So it will be y minus y coordinate equals slope x minus x coordinate, so it's +3. And simplify it, so it's y equals 3/2 x plus 9/2. And then it's +4, but we want denominator 2, so it will be 8/2. Therefore, our final line is of the form 3/2 x plus 17/2. Since we have a piece of graph paper, we may want to look at the geometry of this question. So we have this line. Since the slope-intercept form makes it easier to graph, we'll refer to this equation. So we start with -2.5, which is somewhere here, -5/2. We go by the slope 3/2, so 2 across 3 up, 2, 3 here, and again 2 across 3 up, and draw a line. So our line looks somehow like this. Now this is not the final line. The question calls for a line that is parallel to it, but comes through the point -3, 4. So -3, 4 is actually here, and we want to graph parallel. So the slope of it should be the same, 3/2, 2 across 3 up, 1, 2, 3 approximately here, 2 across 3 down. So our line is actually this one. And it happens that the y-intercept would be 8.5. So that makes some sort of sense. This is 5, 6, 7, 8.5. Most likely that would be here. So this was given line, and that's the line that we're looking for. This one. The next example gives us some nice applications of linear function. A rock attached to a string is whirled horizontally about the origin O in a counterclockwise circular path with radius 5 feet. So the rock goes like this. When the string breaks, the rock travels on a linear path perpendicular to the radius OP. This is radius OP, perpendicular to it, and hits a wall located at y equals 10 feet. This is 10. If the string breaks when the rock is at point 34, so the coordinates of this point when the string breaks are given, 34, find the x-coordinate of the point at which the rock hits the wall. Oh, so we need to find the x-coordinate of this particular point. We know that the y-coordinate is 10. We need x-coordinate of it. So what would be the good plan? If I will be able to write the equation of a line that is perpendicular to the radius at this point 3/4, then I will be able to find out this x-coordinate of the point that hits the level 10. So let's focus on how to write the equation of this line. Well, we need the slope, but it's perpendicular to this particular line. So what's the slope of OP? Well, this slope is really rise over run. So it's 4/3. The slope is 4/3. Therefore, the perpendicular slope equals negative reciprocal, so -3/4. So now we have a slope, and we also have a point that the line must go through. It's a point 3/4. So now we can start writing our equation. Y minus y coordinate equals your slope, -3/4, x minus x coordinate. Let's simplify this. -3/4 x plus 9/4 plus 4, but instead of 4 we'll write 16/4 because we want to prepare our ground to add these two fractions. So y equals -3/4 x plus 25/4. That's the equation of our line, which is this one. And now we need to figure out for what kind of x the value of this line is equal to 10. So if y equals 10, then find x from the equation -3/4 x plus 25/4. So 3/4 x equals 25/4 minus 10, which is 40/4. We can multiply the whole equation by 4, and we have 3x equals 25 minus 40, which is -15, and finally x is -5. So we know that the rock hits the wall at the x-coordinate equals -5, exactly here. It makes sense with this diagram. Here we have another application. A manufacturer finds that the costs incurred in the manufacture and sale of a particular type of calculator are $180,000 plus $27 per calculator. Determine the profit function P, given that X calculators are manufactured and sold at $59 each. So what's a profit? Profit is the revenue minus the cost. We would like to have profit as a function of the number of calculators sold. So P of X equals, what will be the revenue if we sell X calculators? Well, they are sold for $59, so it's 59X. And now what would be the cost? Since each calculator costs $27 to produce, we need to subtract 27 times X. That's the cost of producing X calculators, plus the fixed cost, which is $180,000. This is something that we need to start with, no matter how many calculators we're going to produce. So overall, this function is 59 minus 27 is 32x minus 180,000. So that's our profit function. And this profit function on the diagram is marked in blue. That's a blue line here. Determine the break-even point. The break-even point is actually the point when the profit is 0. So we want such an x that P of x equals to 0. Okay, therefore 32x minus 180,000 equals 0. Therefore x equals 180,000 over 32, which turned out to be 5625. What does this mean? That means that we need to produce 5,625 calculators to cover the cost and not to earn any money, but also not to lose anything on the production. Let's look again at this diagram. Instead of looking at the profit, we could look at the cost, which is the red line, and revenue, which is the gray line, and the intercept of these two is the break point for 5,625 calculators produced. The revenue would be this much, but also the cost would be the same much. So overall, we are break even. And the last exercise is asking us to determine the slope between two arbitrary chosen points on the graph of parabola x squared plus 1. When one point is with given coordinates 2, 5, and the other point Q is sliding along the parabola closer and closer to the point P, we are going to observe the behavior of the slope. So here the idea is to find out the general formula for the slope PQ, where Q is positioned a little bit farther than 2. So that's first coordinate of P, and Q has first coordinate 2 plus h, 2 plus a little bit. So this distance is the distance h. Therefore, the coordinates of Q are 2 plus h, first coordinate, and to get the second coordinate, you plug it in your 2 plus h inside the formula for the function. So you have 2 plus h squared plus 1. If h is 1, determine the coordinates of Q and the slope of the secant line. So particularly if this Q has first coordinate 3, because it's 2 plus 1, what is the second coordinate? And what is the slope between PQ? So Q will have coordinates 3, and then plug it in 1 here, so you have 2 plus 1 is 3 squared plus 1, which really is 3 and 10. Okay, so the second coordinate of Q is 10. So now let's try to calculate slope of the segment PQ, but maybe I will write a subindex when h equals 1 to distinguish it from the following calculations when h will be different. So this slope is the difference quotient between the points 3, 10 and 2, 5. So difference in y is 10 minus 5 over 3 minus 2. So we really have 5. The slope of PQ when h is 1 is equal 5. Do the same for h equals 0.1. So let's calculate slope of PQ when h equals 0.1. In order to do that, I really need the coordinates of the point Q when h is 0.1, so the x-coordinate will be 2 plus 0.1, 2.1, and the y-coordinate would be 2.1 square plus 1. That gives me the point 2.1 and 541 using calculator. So we're ready to calculate the slope, and we have 541 minus 5 over 2.1 minus 2, which is 0.41 over 0.1, which is actually 4.1. So the slope is a little bit less steep. And we can imagine that if Q is closer, for example, somewhere there, we can draw the secant line like this, and obviously the slope of this particular secant line will be a lot smaller. It wasn't 5, it's 4.1. Then imagine that this point can go closer and closer to P, as close as we want to. We still need 2 points in order to calculate slope, but we can observe the limiting value, and this limiting value will be very close to something that's called tangent line. Tangent line, that means the line that touches this graph only in one place. Okay, so the next step would be to perform the same calculations for h equals 0.01, and maybe even closer 0.001, and even closer 0.0001. Since those calculations are repeating itself, maybe it's a good idea to use a graphing calculator and produce a list of numbers. So what would we use for a formula to plug it into the graphing calculator? Well, what did we do to find out the slope? We've been using the point Q with new h. So instead of h, we're going to use x. So in the graphing calculator, under y1, we may want to write down the formula like this. 2 plus x instead of h square plus 1 minus the second coordinate of the P point, which is 5, everything over 2 plus x minus 2. That simplifies to 2 plus x square minus 4 over x. And then remember, this x plays the role of h, and it's enough to change the h into 0.01, and this will produce the slope of the segment PQ, where h is equal to 0.01. We also can produce some other values for different h's. So let's look at the graphing calculator. So we can plug it in the formula. That will be 2 plus x squared minus 4 divided by x. And then we can use table of values, and we can produce the slopes for different h, which in this case is x. So if x was 1, we calculate the slope is 5, and we have a confirmation. If h was 0.1, then the value of slope turned out 4.1. Now we want to calculate when h is 0.01, closer to point P, then the slope turned out to be 4.01, and even closer 0.001, the slope will be even closer to 4.001. If we want even closer, 0.0001, the slope will be nearly 4. So we can predict that the closer the Q is to P, that means if we approach the tangent line, the slope of the tangent line will be 4. So let's record on the side what did we come up with the calculator. If h was 1, then the slope was 5. If h is 0.1, then the slope becomes 4.1. If h is closer 0.01, then the slope is 4.01. If h is 0.001, then the slope is 4.001. And we can predict that the slope of the tangent line is actually equal 4. So we can come back to finish this equation. Slope of PQ when h is 0.01, it was 4.01. As h approaches 0, what value does the slope of the secant line seem to be approaching? That's the value 4 that we come up with here. And as a last task, we need to verify that the slope of the line passing through these two given points is actually 4 plus h. Well, let's calculate slope generally looking at these 2 points. So that will be the second coordinate of the point Q plus 1 minus second coordinate of point P over first coordinate of Q minus first coordinate of P. Now, raise it to the square, so we have 4 plus 4h plus h squared minus 4 over, these two 2's are gone, so we end up just with h, and the 2 4's are gone, so we end up with 4h plus h squared. Let's factor 1h and simplify it with the denominator, and yes, we end up with 4 plus h as desired. Now it's very easy to understand why did the limiting value of our slopes was approaching 4. Because if h is going closer and closer to 0, then 4 plus h is going closer and closer to 4.